All right, so where we left off yesterday was that we learned about the concept of induction and figured out that when we were dealing with alternating current circuits, we were going to have a difficulty because the voltage drops across different elements of our circuits are going to have different timing. So that sometimes what will happen is the voltage drop across, let's say, a resistor might be at its largest value at the same time that the voltage drop across, say, an inductor might be really, really positive, really, really negative. And so what that means is that when you try to apply the loop rule, it gets really complicated because you're going to have a hard time syncing up mathematically all these peaks and valleys to the voltages and the current. So we're going to have to find some way to organize the information so that we can think it through and still be able to get the right answer. So here's what we're going to do. When thinking about alternating current circuits, we're going to start simple and think about circuits with one circuit element at a time. So we can hopefully isolate how each of the various things that could be in a circuit might behave. Then what we're going to do is we're going to invent a new kind of math that we can use to talk about what's happening inside those circuits and hopefully bring it all together so that we can take this super, super complicated problem and kind of simplify it down into a form that we can solve relatively easily. By the time we're done, this is going to be super easy. So let's start with the simplest AC circuit that I can possibly have. We're just going to have one AC voltage source connected to a resistor. And let's think about how that's going to play. So here's my AC voltage source. My purple pen is dying. So now, remember, this is an alternating current voltage source. So this is like a battery, except the voltage of that battery would go something like the EMF of the battery would be some V max times, let's go with the sine. It's either a sine or a cosine, and it doesn't especially matter. Where again, how this omega t is going to work is your voltage is going to make kind of a sine wave. And what this omega factor does is it alters the periodicity of your function so that if omega is very, very large, it's going to repeat much more frequently. Imagine that I had another battery where the omega was a larger number. Then what would happen is it would go to the same size heights and same depths, but the period would be shorter. So this is a large value of omega. And the black line would be a smaller omega. So conceptually, that's what omega represents. And for AC circuits here in the United States, the standard value for omega is about 377. And the reason for that is because omega is equal to 2 pi times the frequency that we alternate with. The frequency is the number of peaks per second of time. And in the US, we tend to use a frequency of 60 hertz. So regardless, we're going to have a voltage that looks something like this, right? Where it's going to go up and down. And of course, We know that the voltage across a resistor, I'm going to call that V sub R, so the voltage drop across the resistor, from Ohm's law is just equal to I times R. We also know from the loop rule that if I go around this circuit at any given moment, the total voltage has to equal 0, which means when the voltage across the battery is really, really large, when this reaches its peak, the voltage across the resistor is going to have to reach its peak as well. So they're going to both rise and fall together. When this voltage from the battery is big, the voltage across the resistor will also be big. And the only way that can work, since R is a constant, is if the current is itself a function with the same periodicity. In other words, it's got the same sine omega t factor here that this does over here. And so as a consequence, if you were to look at a graph for this circuit, the voltage across the battery is going to be some kind of sine wave. And the voltage across, or should be the current, is going to be 0 at the same time that this one, the other one is 0. It's going to be at its maximum at the same time that one is its maximum. It's going to cross 0. It's basically the same curve, just with a different height. So their peaks will happen at the same time, their valleys will happen at the same time, their zeros will happen at the same time. When this sort of condition is met, we say that the current and the voltage are in phase. Right, that's the term that we'll use. So that's cool. That means resistors are super easy to wrap our heads around, because the voltage, when the battery is putting out the biggest amount of voltage, that's also when we're going to get the biggest amount of current. They're going to rise and fall in unison. Now, we can put other things in these circuits. Let's try breaking the same kind of idea down, but let's replace the resistor with a capacitor. So again, I've got an AC voltage source. And a capacitor here. And what's going to happen there is, if you recall, the voltage drop across a capacitor is equal to Q over C. This is just the definition of capacitance kind of rearranged a little bit. We saw that back when we did RC circuits in a previous chapter. So what's going to happen is, for a capacitor, the voltage is going to be largest across that capacitor when the charge on the capacitor is at its biggest. And so when this is putting out the biggest voltage, I'm going to have the biggest amount of charge on the capacitor. However, we also remember from RC circuits how capacitors behaved. Because what's going to happen is, the bigger voltage there is across this capacitor, the harder it is for the battery to put more charge on the capacitor, right? There's a whole lot of charge built up on the capacitor, and when the battery tries to push out more positive charge, the charge that's already on the capacitor is repelling it via the Coulomb force. And so what's going to happen is, the more charge you've got, the smaller the current tends to be. That's why when we deal with RC circuits, what happens is, the charge for an RC circuit where there's just a DC battery, the charge kind of does this, and the current kind of does this. So when the charge is big, the current is low. When the charge is small, the current is high. But what that means is that when the voltage across this is large, and therefore the voltage across this is large, the current will not be large. So unlike the resistor, where when the voltage was big, the current was also big, here what's going to happen is the current and the voltage are going to get big at different moments. We're going to say that these two things are out of phase. And in fact, when the voltage is at its maximum, that's when the current is down here at 0. So they're super out of phase. And so what's going to happen is if I were to do a graph of the current versus the voltage for a capacitor, here's how this is going to play out. Imagine that this is the voltage across my capacitor, and therefore across the battery, same thing. Right? It looks like a happy sine wave, so that the EMF is going to be something like V max sine omega t. If I'm looking at the current in the circuit, it's not going to line up. The peaks are not going to line up with the peaks of the voltage. The current is going to end up shifted a little one way or the other. And the way that's going to work is when, let's see, make sure you get this right. When, okay, the current has to lead the voltage. So when the voltage across the battery is still at 0, the current in my circuit is going to be really, really large. By the time the voltage reaches its peak, the current will have dropped down to 0. By the time the voltage has dropped back down to 0, the current will have switched and reached its maximum. And so what you've got is the same shape curve for the current, except it's like the whole curve has been shifted to the left. So what we say is that the current and the voltage are out of phase. Now, if you think about the unit circle for a second, to go from 0 to full, that's like 90 degrees on the unit circle. So we say in this case here, this shift is a full 90 degrees out of phase, which is the same as pi over 2 radians. So with a capacitor, we say that a capacitor is 90 degrees out of phase between the current and the voltage. And you'll notice the way we've graphed this, the current is maxing out before the voltage maxes out. So we say that in this case here, the current leads the voltage. And for capacitors, that's usually how that plays out. The current and voltage are exactly 90 degrees or pi over 2 radians out of phase, with the current leading the voltage. Now, that gives us a little bit of insight about the timing. It doesn't give us much insight about the size. So we'll think about the size of that voltage drop as well here in a minute. Let's go back and think about what happens if we replace this with an inductor. So same scenario. And again, what's going to happen is the voltage across my battery, of course, because of the loop rule, this voltage has to be the same as this voltage. It's going to be some kind of sinusoidal oscillation from negative Vmax to positive Vmax. But now let's think about the voltage drop across an inductor. Well, from Faraday's law, we know that across an inductor, we know that the voltage across an inductor is negative delta I over delta T. Now, L is the inductance, which is just some number that got determined when we built that particular coil, right? It has to do with the size and the shape of the coil. We saw that in the previous lecture. It's just a number. Delta I over delta T, though, the way I interpret that is it's the slope. It's the rate of change of my current graph. So this current graph that I'm trying to derive is going to be interesting because when the voltage is big, then the slope of my current graph has to be big. And when the voltage is zero, the slope of my current is going to have to be zero. Except, wait a second. We know that my current graph is going to be some kind of sinusoidal shape, right? And when you think about the slope of a curve, it's like you draw a tangent line at that point. And so what's going to happen is when the slope of my current is really, really big, that means that my graph is going to be super steep. That's a large slope. This is a zero slope. This is a negative slope. So think about it this way. When I look at this peak right here, that peak has the voltage being really, really big. But that tells me that if the voltage is really, really big, the slope of my current graph has to be really, really big, which means my current graph is going to have to be super slopey. Does that make sense? But right here, the voltage is zero. When the voltage is zero, the slope's got to be zero. That means that my current graph has to be flat. Here, big and negative, big and negative. Here it's zero. And so what you see is that I get a curve, and again, it looks like it's been shifted out of phase a little bit. And in fact, it's been shifted 90 degrees out of phase, but unlike the capacitor, it's been shifted 90 degrees the other direction. Here, the voltage is hitting its peak, and then a little bit later, the current hits its peak. So for an inductor, we say that inductors, the current and the voltage are, again, 90 degrees, or pi over 2 radians, out of phase. But here, the voltage leads the current. Or sometimes we'll say the current lags the voltage. And so when we talk about AC circuits, very frequently you'll talk about either the current or the voltage lagging or leading the other. And it's all boiling down to the fact that sometimes you'll end up with the voltage maxing out before the current. Other times the voltage will max out after the current. And other times, like in the case of resistors, they will max out at the same moment. And so dealing with that timing is going to end up being a critically important question. And you will frequently be asked to figure out by how much does the current lag or lead. It won't always be 90 degrees in more complicated circuits. But if I have nothing but an inductor or nothing but a capacitor, they will always be 90 degrees out of phase. A quick way of remembering like which direction the shifts occur is the mnemonic device Eli the Iceman. This is how I keep it straight when I'm drawing these stupid graphs. So for an inductor L, the EMF or the voltage is going to lead the current. So the voltage came before the current. However, for a capacitor, the current is before the EMF or the voltage. So here, the current leads the voltage. So if you're ever not sure which direction those shifts are going, just remember Eli the Iceman, and you can figure out which one is which. You know they're both 90 degrees, but this one tells you which one goes to the left and which one goes to the right. So now we've got this timing thing figured out. But what we haven't figured out is the sizing thing, like how big are these voltage drops going to be? And if we go back to the resistor, well, we know that resistors obey Ohm's law, right? V equals I times R. So the voltage drop across the resistor gets bigger with the current. Cool. And that's going to be similarly true for an AC circuit. It's going to work just as well for an AC circuit as it does for a DC circuit. And Ohm's law is super easy to use. However, for capacitors and inductors, we don't yet have an equivalent. And what's going to happen is, I have a voltage drop expression, but the voltage isn't related to the current. It's related to the amount of charge on the capacitor. And it would be super awesome if I could figure out a way of kind of finding like a version of Ohm's law that relates the current and the voltage to each other, but for a capacitor. So we're just going to make one up. We're going to kind of cheat a little bit by creating something that's going to be kind of like resistance, but it's going to be the effective resistance of a capacitor. Now, here's what's going to make that tricky, right? Theoretically, what that would look like is I could say that the voltage drop across my capacitor is just going to equal the current times whatever the heck this thing is that's going to be kind of like a resistance. I'm just going to call it X, simply X sub C, since we're talking about capacitance. We're going to do the same thing with inductors here in a minute. So we're going to hypothesize that there exists some quantity that is like resistance. It's going to have the same units as resistance, and it's going to basically be a thing that relates how much current I get to how much voltage I've got. The idea is if I have a bigger battery, I'll get more current going through this circuit, and if I have a smaller battery, I'll have less current, just like you would with a resistor. We're going to imagine that this is a thing that we could come up with. But what's going to make this tricky is, again, we know that the amount of, if this is the charge Q and this is the current I, the thing that we know is that the bigger the charge gets, the smaller the current gets. Because the more charge is built up here, the harder the capacitor pushes back against the battery, and therefore the more difficult it is to squeeze current out. So this hypothetical quantity that we're going to come up with, it's going to be weird. And one way to think about it is that these graphs are for DC circuits. These are for circuits where the charge always comes out of the battery and it only is ever flowing in one direction. But in an alternating current circuit, what's going to happen is the charge is going to flow in one direction, but then it's going to turn around and flow the other direction. So in an AC circuit, what's going to happen is I'm going to be putting charge on the capacitor, then pulling charge off the capacitor. So it's going to be like this charging graph, but it's only going to charge up part of the time, and then it's going to discharge part of the time, up, down, and the charge is never going to get very large. Now, in an AC circuit, you're switching direction with some frequency. Maybe you're switching direction with 60 hertz, so 60 times every second. You're flipping directions, and the capacitor stops charging up and starts charging back down. If that frequency were low, that means that you're going forward for a long time and then slowing back down after a long time. That would have the thing charge up for a longer amount of time and discharge for a longer amount of time. the switches would happen less frequency. And you'll notice that when this happens, if I charge up for a longer time, I can get more charge on the capacitor. If I get more charge on the capacitor, I'm going to get less current. So what's going to happen here is this XC thing that we're inventing, it's going to depend on the frequency that my AC circuit operates at. At a high frequency, I'm not going to barely move any charge onto the capacitor, and then it's going to start immediately coming back off again. And if Q never gets very big, then the voltage drop never gets very big, and I can get a lot of current. If, however, I allow it to charge up for a very, very long time, Q is going to get super, super big. I'm going to push back against the battery super, super hard, and the current's never going to be very large. So this quantity is going to be larger at low frequencies and smaller at high frequencies. At high frequencies, this thing barely pushes back at all. This is barely going to offer any resistance at all. Now, I can't derive it for you, but hopefully I've at least motivated the fact that there should be a frequency dependence for this capacitor. So this X sub C thing that we're inventing to make our lives easier, we're going to give it a name. We're going to call it the capacitive reactance. But reactance is just kind of like resistance. It's the resistance, in quotation marks, of a capacitor in an AC circuit. It's got the same units as resistance. You measure it in ohms. Its origin comes from something different. So it's not truly resistance, but it behaves like a resistance. So it's going to be treated like one. And we can say that this capacitive reactance ends up being 1 over omega times C, where again, omega is that 2 pi times the frequency. So what happens is, if the frequency is really, really big, if I'm switching back and forth very, very rapidly, I have a huge number down here. XC is tiny, so it's gonna offer a small resistance if that's the case. Now, the reason C is on the bottom is because if I have a large capacitance, that means that my time constant is also very large. And so it takes a long time to ramp up that charging curve. If I have a small capacitance, the capacitor charges up super, super fast. And once it gets charged up, it pushes back really, really hard. So having a large capacitance means that you could get a whole lot more charge before the voltage gets very big. And that's why C is on the bottom. So, super neat. Now, if we could do this with capacitance, we could do this with inductance as well. So we're going to invent XL, which is going to be the inductive reactance. And the inductive reactance is going to be more of the same, right? The inductive reactance is going to be like the effective resistance of an inductor. Now, to remind you, for an inductor, the voltage drop across it is related to the rate at which the current is changing. And remember, the bigger voltage drop across this, the more the reactance is going to be. If you have a big voltage drop, that means that your inductor is pushing back against the battery super, super hard, and the battery won't be able to squeeze much current out. So anything that makes this voltage get bigger makes my reactance get larger. Now notice L. If L gets bigger, that's going to get bigger, right? So the inductive reactance is going to depend on L. L, larger inductive reactance. So already I can tell that XL is going to be related to L. But what about the frequency? Well, Remember, delta I over delta T is the rate at which the current is changing. Now, if my current only goes from positive to negative once every 5 seconds, that means that the current is going to change once every 5 seconds. It's going to change super, 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 super slowly. But if my current is going from positive to negative 100 times per second, if I'm at a frequency of 100 hertz, then what's going to happen is it's got to change super, super rapidly to get all those changes in. So delta I over delta T is going to be super, super big for a super big frequency, which means larger frequencies are going to give me a larger reactance. So unlike the capacitor, where omega shows up on the denominator, here, omega is going to show up here up top. So larger frequencies, larger inductive reactance. And the reason this is cool is because now what's going to happen is if we've sort of reduced all the weird, complicated average jitter in all these things to one value, if I'm thinking about an AC circuit that has resistors, inductors, and capacitors, we would call this a series RLC circuit because it's got everything. Well, what's going to happen is the loop rule just has, here's my V total, and here's my voltage drop across the resistor, and here's a voltage drop across the inductor, and here's a voltage drop across the capacitor. And what's going to happen is at any given moment, V total minus VR minus VL minus VC has to be 0. That's the loop rule, right? And of course, that means that V total would have to equal the sum of VR plus VL plus VC. So all the voltage drops at any given moment have to add up to V total. And of course, I can find these voltage drops using these expressions, or in this case, Ohm's law. Now, the complicating factor, though, is the timing thing, right? The fact that these two guys here are not in phase with this guy here. And that means that when I try to do this addition, I can't do like regular straight up addition. I have to do something more complicated than that, because technically this is something that goes as like a sine wave. This is something that goes like a sine wave also. This goes as a sine wave shifted forward in time 90 degrees. This goes as a sine wave shifted backwards in time 90 degrees. Oh my God, what a mess. So here's where we're going to get kind of inventive with our math so that we can do this sum in a way that doesn't cause my brain to explode. And to do that, we're going to invent something called a phasor diagram. And here's the idea behind a phasor diagram. So phasor diagrams are used to describe quantities like these, where you have some maximum amount, and it's going to go from positive to negative, like sinusoidally. Anything that changes like a sine wave can be described by a phasor diagram. And the idea is that we're going to represent whatever it is we're talking about with an arrow, much like a vector. And the length of that arrow is going to scale to the maximum of whatever it is we're talking about. So if I was using a phasor diagram to describe the current in an AC circuit, and I knew that that current looked like this, for instance, where at its maximum, the current was, let's say, 5 amps. And at its minimum, the current was like negative 5 amps. Then what I would do is I would describe this current by drawing an arrow and having it be 5 units long, 1 for every amp. So here's my arrow, and it's 5 units long. Now, here's what we're going to do. And here's my y-axis. Here's my x-axis. What I'm going to do is I'm going to allow this arrow to spin. So in my imagination, this arrow is going to be spinning constantly at a certain rate. And what's going to happen is the value of the current is going to be one component of whatever my thing is. Let's go for this one, and it depends on how you set this up. A lot of people use the y component, others will use the x component. For reasons that hopefully will become apparent in a minute, let's use the y component for this. So the idea is that as this arrow rotates, at any given moment, the y component of that arrow is what the current is actually doing. So notice, the way I have it drawn here, right now, my arrow is completely sideways, which means it's got 5 units in the x direction, but 0 units in the y direction. And lo and behold, at that moment, the current equals 0. Now what's going to happen is a little bit later, this thing will have rotated, and we're going to spin it at an angular velocity of omega. Remember, we used that same symbol omega for the angular velocity back in chapter 10 last semester. And so it kind of makes sense, because what's going to happen is, it's going to rotate and it will go through some angle, and that angle is going to end up being omega times however much time has elapsed. So it's spinning at a constant rate. And so a little time later, what's going to happen is now this thing is diagonal. It's still 5 units long, but now this right here is the y component. And so this would be how high we are on the graph. We'd be less than 5, because if you wait a little bit longer and the arrow points straight up, well, now this is a full 5 units. That's going to correspond to this moment. When it rotates even further, now it's back down to 0. When it rotates even further, now the y component is something negative. So now I'm down here. When it rotates down to here, it's at my negative peak. And so as this thing spins around, the y component is going to trace out exactly this stupid graph. So hopefully that was clear from my crummy drawings. But just in case, and I hope this is the one that I want, here's somebody else who has done a groovy little kind of animation to sort of make the point. And you can see that what they've got there in this animation is this little red arrow, this little red line, that's like maybe our current. And as it spins around, they're tracing out the y component. That's the little pink line is the y component. And you can see that when the pink line is big and positive, the sine wave is at its maximum. When the pink line is big and negative, it's at its minimum. And when this thing is completely sideways, that's when my graph is crossing 0. So we're representing this graph that changes with time just by taking an arrow of a certain length and having it spin at a constant speed. And we can do that with anything. So when I'm dealing with this loop rule problem that's so intractable, what's going to happen is the VR, the VL, the VC, all of those I can represent by phasors. Each of those is going to be rotating around, and that's cool. But remember, what's going to happen is the phase of each of those is different. So if I go back to these phasors, what's going to happen Oh, darn it. You've made me sad. That was my go-to place, and now it's gone. All right. So what's going to happen? Yeah, this is my go-to. So let's go back and think about how phasors will play out with what we've seen so far. We saw that resistors are always in phase. Oh, my battery's running low. Hang on. Ah! Not plugged in this morning. There we go. So for a resistor, the current going in through the circuit, the resistor, and the voltage across the battery are always in phase. So if I was drawing phasors for both of those things at the same time, they would be two arrows that would both always be pointing the same direction. So you can see that that's what they've done in this diagram here, right? The black line is the current in the circuit, and the kind of reddish brown line is the voltage across the resistor. And because those two things are in phase, they've drawn their two phasors so they're pointing the same direction. And as time goes on, they're always going to be in phase. They're going to rotate together and both go up and both go down, both be zero, all at the same moments. So that's what you see for that resistor circuit, is the current and the voltage are always going to rotate together. However, if I'm dealing with a capacitor, for a capacitor, remember, the current is going to lead the voltage, and the capacitor is going to be out of phase by 90 degrees. So if I'm drawing a phasor diagram for these two guys, what's going to happen is you can see that my current, I've started my current going this way, and I've got my voltage across the capacitor a full 90 degrees behind it. And so now what's going to happen is, as I rotate them, they're going to always be at 90 degrees with respect to one another as they turn. They're going to rotate together. And so as you watch, they're both spinning at the same rate, but it's causing the peaks to happen at different moments, right? First, the current will peak, then the voltage will peak. Now, what about the inductor? Well, the inductors are also 90 degrees out of phase. So here, the green line is the voltage across the inductor. The black line is still the current. But now you can see that because it's out of phase the other direction from capacitors, it's going to be 90 degrees ahead of the current. But still, they're going to rotate at the exact same rate. Now, what's cool about these phasor diagrams is that, remember, what I'm trying to pull off here is I'm trying to add up VC, VL, and VR that are all three out of phase with each other. So what if I put all three of those on a phasor diagram at the same time? Well, I'd have arrows, but what's going to happen is VR is going to point one direction, VC is going to point one direction, VL is going to point the other direction. All three of them are going to be perpendicular to each other. It's going to look something like here we go. Now, this is the bunch of crazy looking sine waves that are too hard for me to think of, to keep track of. It's an absolute crazy thing to keep track of. But if I think about it in terms of phasors, it's easy. So for this one here, they're using this brown line to represent the voltage across the resistor. And of course, the current would be the same direction as this. The green line is the voltage across the inductor, which is 90 degrees ahead of the voltage across the resistor. The blue line is the voltage across the capacitor, which is 90 degrees behind the voltage across the resistor. So the three of those things are all perpendicular to each other. Now, this red line, that's V total. Because remember, what are we trying to draw here? We're trying to add, we know that VR plus VL plus VC should equal V total. And when we draw them like phasors, what we realize is that they look just like vectors. And we're going to do this addition the same way that we would add a bunch of vectors. So what's going to happen is how do you add vectors? You put them tail to tip. So in our diagram, we had VR being this way and VL being this way. And they had VL being super big in the picture. VC they had being this way, and for their particular circuit, VC was smaller than VL, probably because the inductive capacitance was bigger than the capacitive reactance. Inductive reactance was bigger than the capacitive reactance. Yeah, split the tongue there. That doesn't have to be that way, but we're going to do it this way just for convenience sake. So if I wanted to add these three vectors together and get V total, what I would do is I'd put them all tail to tip. So I'd slide this little guy and put him tail to tip with that. And then I'd slide this little guy, put him tail to tip with that. And so V total would therefore go from the tail of the first vector to the tip of the last vector. So this right here would be V total. And that's why in their animation, they have this red arrow. This red arrow is V total. It's just what you would get if you scooted this guy and put him tail to tip with that and put this guy tail to tip with that. It's the total there. But notice what's going to happen is as I rotate, all three of those things are going to end up rotating together. So if I wanted to do VR plus VC plus VL to find, say, the magnitude of V total, I could just do the vector math and it's going to be the same at any given moment in time. And so that's our goal. That's how we're going to do this. Wrong screen share, stupid. Technical difficulties, please stand by. Messy table, messy table. So that's our goal. We want to add these three things together. And of course, we know how to add vectors, right? What you do is you add the X components to the X components and the Y components to the Y components. And the way I have it drawn right here, VR is in the X direction, VL and VC are both in the Y direction. So I could say that this, from the Pythagorean theorem, would equal VR squared plus, I got to subtract VL and VC, so VL minus VC quantity squared. Again, I'm just using the Pythagorean theorem because I have VR on this side and this distance right here is VL minus VC. So that's this distance right here. So this squared plus this squared equals that squared. And so I have a relationship between VR, VL, VC, and V total. But now what's going to happen is I would very much like to have a kind of an AC circuit version of Ohm's law, right? Remember, for Ohm's law, V equals I times R, right? And for these, this is true for the resistor. For VL, we're going to say that that's going to equal I times that inductive reactance. For VC, that's going to equal I times the capacitive reactance. And so let's just play with that. here I got V total. And in here, I'm going to have VR squared. That's going to be I squared R squared. And over here, that's going to be I times XL minus I times XC quantity squared. And the thing is that I've got I's all over the place, right? I could factor an I out of this, but since I'm factoring it out of that square, it's going to come out squared. Well, now I have I squareds both places. Let's just factor them all the way out of the radical. When I come out of the radical, I'll have to square root that I, so it's going to come out as a single I, not a squared I. So now I've got V total equals I times the square root of whatever R squared is. And so what we've got right now is something that kind of looks a little sort of maybe like Ohm's law, because I got V equals I times something ugly, but that something ugly has units of ohms, right? That's got ohms as a unit. That's got ohms as a unit. So this thing right here it's like a resistance, but it's a resistance that depends not just on the resistance of the resistors, but also on the reactances of the inductors and the capacitors. It's an effective resistance. So we're going to give this big radical thing a name. We're going to call that Z, the impedance of the circuit. So Z is going to equal the square root of R squared plus XL minus XC. Again, just like resistance, it's going to have units of ohms. It's measured in ohms. And it's going to allow us to get a very simple relationship between the voltage of my battery and the amount of current that I get in my circuit. And here's the cool part. If I tell you the RMS, or the average voltage in my circuit, then I'm going to get out the RMS, or the average current in my circuit. If I tell you the peak voltage, I'm going to get out the peak current. So it's going to allow me to do a lot of this math with one number, even though all these things are changing in some weird, crazy, complicated way. So that's the impedance of an AC circuit. Super easy. We can do this in our sleep. Now, let's do a quick example. Let's imagine that I've got a series RLC circuit. And I hook it up to the wall. And the wall power is going to be 120 volts at a frequency of 60 hertz. Right? That's pretty standard in the walls of every house in America. I've got a resistor. I've got a capacitor. I've got an inductor. And let's say that this resistor is 1,000 ohms. And let's imagine this inductor is, I don't know, something like 5 henries. And this capacitor doing math so I don't get stupid. I want the numbers to fall in a certain range, so I've got to figure out where I want the answer to be. and then come up with a question. So I have a bad habit of making numbers up on the fly and them not working well. So real quick. So let's go with 5. There we go. That should work. So I've got this circuit. And what I'd like to know is how much current am I going to get in this circuit? So I want to find the RMS current in this circuit. Now, how will I do that? Well, I know the resistance, the capacitance, and the inductance, and I also know the frequency. This is F. So the first thing I'm going to do is I'm going to figure out the impedance of this circuit. That's going to be the effective resistance of these 3 guys acting together, even though they're all out of phase with each other. On average, it's going to work out to a certain number for the resistance. So R is easy. That's this. Now, to get XL, there's going to be XC. XC is going to be 1 over omega times C. Now, what's omega? Well, omega is 2 pi times F. So 2 times pi times F times C. So 2 pi times 60 hertz. And C is 5 microfarads. That's 5 times 10 to the negative 6. So in this circuit, XC works out to be about 530 ohms. 0.5. There we go. Super easy, right? Now, what about the inductive reactance? What's XL going to be? Well, that's going to be omega times L, or 2 pi F times L. So 2 times pi times 60 times L, we said, was 5. And when I work that out, I get about 1,884 ohms. So now I've got 1,000 ohms from my resistor. I've got 530.5 ohms for my capacitor and 1,884 ohms for my inductor. But my total impedance, which is the total of all of that, I can't just do straight math because they're all out of phase. Instead, I'll use this, where R is equal to 1,000, XL is equal to 1,884, and XC is equal to 530. And when I do all of that, my total impedance is 1,682 ohms. And since I know that V equals I times not R, but Z, my current is going to equal my V total over Z, which is 120 volts RMS divided by 1682. And I get 0.0713 amps. This is my RMS current because I used my RMS voltage. It's the average voltage over time. And I was able to figure all of that out without ever having to concern myself overly much about what the current was at a particular moment. I didn't have to worry about that annoying sine function because I'm averaging it all out. So I can do this kind of stuff super, super easily. It's not very challenging. Now, there is one small complication, and that complication hopefully should have been apparent when I drew that little phasor diagram earlier. Because remember, the current in my circuit is always in phase with the resistor. So if this is VR, I could imagine my current being a little phasor in the same direction. But notice in this diagram, VR is in phase with that. VL is 90 degrees out of phase, which we expected. VC is 90 degrees out of phase. But look at V total. V total is out of phase, but it's not 90 degrees out of phase. It's only some smaller amount. We'll call that angle phi out of phase. We call that the phase angle of my AC circuit. And what's going to happen is for my voltage source, my battery, it's going to be out of phase with the current, but it won't necessarily be a full 90 degrees. It may be something between 0 and 90 degrees. Plus, and this is important, when we drew this phasor diagram, we assumed that VL was bigger than VC, right? I drew a bigger arrow for VL than I drew for VC. And as a consequence, when I subtracted VC and VL, I got a positive amount. But there's no reason why that has to be the case. I could always imagine a circuit where VC is way, way big and VL is very, very small. But if that's the case, then VL would have been a small amount up and VC would have been a whole lot down. My V total might have been down here, which means I could have had a phase angle where the current is ahead of the voltage, as opposed to the original case where the voltage was ahead of the current. So in an AC circuit, sometimes the current will either lag or lead the voltage by some angle other than 90 once you do all the math. And it's often important to know what that phase angle is. How would I figure that out? Well, in either case, what's going to happen is I've got this little triangle there, right? And what's going to happen is the tangent of that angle is going to be the length of this side. That's the opposite side. But that is just XL minus XC divided by the length of this side, R. So if I want to find the phase angle for that circuit, that's how I would do it. Notice if the phase angle is positive, that tells me that the voltage leads the current. And if the phase angle is negative, that tells me that the voltage lags the current. Now, for this example we just did, what's that phase angle going to look like? Well, in this case, what's going to happen is the tangent of that phase angle is going to equal XL, which was 1884, minus only 530 over 1,000. So when I use the inverse tangent to solve for that expression, I get that it's positive 53.5 degrees. And so we would say that in this particular example, since the phase angle is positive, that means that we have something very similar to our original picture where V total is up here in the positive region, not down here in the negative region. And our voltage leads the current. And that's going to always happen anytime XL is bigger than XC. If XC was bigger than XL, then obviously this difference up top would be a negative number, and I'd have a negative phase angle. So if my capacitive reactance is bigger than my inductive reactance, the current will lead the voltage. if the capacitive reactance is smaller than the inductive reactance, it'll be the other way around. So super, super nifty. So one thing that's kind of cool about AC circuits is that the amount of current you get is going to end up depending on what frequency you're operating at. We operated this at 60 hertz, and we got that much current. Would it be possible to get more current out of the circuit? Could I perhaps squeeze a bit more current out of the circuit just by changing the frequency? So I'm not making the battery stronger, and I'm not going to change the values of R or C or L, but I would think about changing the frequency at which I'm operating. Could I pull that off? Well, one way to think about that is in my impedance. If I can make my impedance be lower, then if the impedance gets lower, the current's going to have to get bigger for this to stay true. And changing the frequency is not going to do anything to R. R doesn't depend on the frequency, but both of these things do. If I increase the frequency, then what's going to happen is XL is going to get bigger and XC is going to get smaller. If I decrease the frequency, it'll be the other way around. And what's going to happen is, in this case, I want this term to get smaller. If I lower my frequency, I'll make this number smaller. I'll make this number bigger. And at some point, XL and XC will be exactly the same. If that's the case, these two terms are going to cancel out. And if they cancel out, that's going to make Z the smallest it ever gets. So at that frequency, I'm going to get more current than I would at our current frequency. So what's that going to look like? Well, if I let XL be the same as XC, and I solve for the frequency at which that will occur, remember XL is omega times L, and XC is 1 over omega times C. Let's get all the omegas together. I'm going to multiply both sides by omega. I'll have omega squared on the left-hand side. Let's divide by L. So omega is going to equal the square root of 1 over LC. And of course, omega is 2 pi F. So the frequency that I'm looking for is this. And we're going to call this the resonant frequency. Now, for this particular circuit, what would my resonant frequency have been? Well, L is 5 and C is 5 times 10 to the minus 6. And then 1 over that is 40,000. The square root of that is 200 divided by 2 pi. I get a resonant frequency of about 31.84. So if I were to cut this frequency from 60 down to 31 and cause my current to change that much more slowly, I would get more current. How much more current would I get? Well, it's super easy, because what's going to happen is at that frequency of 31.84, XL is going to equal XC, right? That means this is going to cancel out. And Z is going to equal the square root of R squared, which is R. And R is 1,000. So yay, I've reduced my impedance down to 1,000. And at that point, 120 divided by 1,000, I do V equals IZ, and I equals V over Z, 120 divided by 1,000 is 0.12 amps, which is clearly bigger than what we were getting before. So yeah, I'm getting more current at that resonant frequency. Now, notice if I lowered the frequency even further, it would not help. Because what's happening is if XL is bigger than XC, then this difference is going to be some non-zero amount. If XC is bigger than XL, this will be a negative number. When I square it, it's going to become some positive non-zero amount. So if XL or XC are different, if one is higher than the other, doesn't matter which way you go, the impedance is going to go up. So this is a local minimum. And what will happen is, if you're looking at the impedance as a function of frequency, what's going to happen is at the resonant frequency, the impedance is going to be some local minimum. It's going to equal whatever R is. And at frequencies higher than that, it's going to get bigger. At frequencies lower than that, it's going to get bigger. And as a consequence, you can't go, you can't just simply say something as simple as, if you raise the frequency, it makes your impedance higher, or if you lower the frequency, it makes your impedance lower. It's not that simple, right? It depends on how close XL and XC are to one another prior to you changing the frequency. Also notice, if I'm at the resonant frequency, what's the phase angle going to be? Well, the phase angle is XL minus XC over R. But if I'm at the resonant frequency, XL and XC are the same, which means this turns into 0. So when you are at the resonant frequency of your circuit, the current going through the circuit and the voltage being provided by my battery are exactly in phase. They are both rising and falling at the same time. When they're out of phase, that's when you're going to get less total current. So one way to think about what's happening there is, when you're at the resonant frequency, your inductor is always trying to push current one direction, but your capacitor is always 180 degrees out of phase with the inductor. So it's like those two voltages are fighting against each other. And if you're out of phase, it means that one of them is fighting harder than the other one. But when you're at the resonant frequency, the inductor and the capacitor are both trying to push current the opposite way of one another, but they're all also fighting equally hard, and they exactly cancel out. And that's what results. So why would I care about this sort of resonant frequency thing? Well, for lots of reasons. One thing to bear in mind is that sometimes you'll have a circuit that could be excited by a number of frequencies at the same time. Case in point, you get in your car and you turn on the radio. Now, around us is this invisible sea of radio waves. Every radio station, every TV station, ham radios, CB radios, tons of different broadcasts have filled the air around us with this invisible sea of electromagnetic radiation. And what's going to happen is the antenna in your car radio is having induced voltages because of this sea of radiation around it. So that antenna is providing kind of a voltage source, an AC voltage source. But different stations are trying to excite it at different frequencies. Now, what I would very much like is for the current to be produced in my car circuitry to represent what is happening at one particular frequency for the one station that I want to listen to. And so what I do is I build a circuit that has a resonant frequency that coincides with my particular radio station. And so what's going to happen is that one frequency will cause lots of current to flow through my speakers, and I'll hear that sound. But the next station over is going to be so far from that resonant frequency that the impedance will be quite large and the current produced will be quite small. It will produce an observable amount of signal in my speakers. How do I change stations? What's happening when I change the station? Well, when I hit the button to change and listen to a different station, what I end up doing is adjusting either L or C. Because remember, the resonant frequency depends on both L and C. One way I could do that is by changing the capacitance. Remember, capacitors are parallel plates. If I make the plates further apart, I just change my capacitance. If I put my plates closer together, I've changed my capacitance. So what I'm doing when I hit that dial is that maybe I'm taking the capacitor and making the plates further apart or closer together so that C changes to a different value and F changes to the new frequency that I'd like to listen to now. So I'm able to tune in to a particular channel by modulating what that resonant frequency is in the circuit. And that's how it works. All right, so I've gammered at you guys enough for today. We'll come back tomorrow, do a little bit more AC circuits, and I think that's good. Take care.